recording?
Yeah, I am.
Cool.
Yeah.
You want to advance through some slides? So before I introduce our speaker, I just wanted to kind of contextualize what it is that we're doing as a society, our efforts here on campus. So what is the Society of Catholic Scientists? Basically, we have Catholics who are also scientists all over the world. This is a surprise to some people that you can have someone that is both Catholic and scientist. And in fact, there are now thousands of us all across the world. This is an international, at this point, organization. And our main focus is to try to promote the idea that faith and science are not mutually exclusive. And in fact, they both are mutually beneficial to help us both live out our faith more fully and to understand how science can allow us to do that. I'm going to advance me here.
Cool.
So yeah, why SCS? I think a lot of us walk through our... how many guys are science majors? How many guys have ever taken a science class?
Hey!
How many guys are kind of lost in the world and trying to figure it all out? It turns out that science is a great way to try to understand God's beautiful creation, and sometimes reflecting on that, whether it's in my class in environmental science, to physics, to biochemistry, wherever it might be, or even in our day-to-day lives, we have this opportunity to use science as a lens to further understand who we are in all this greater creation. So it helps us grow closer to God. So this idea of SCS is a bunch of scientists coming together to promote this idea, but it's also to try to invite you, students, as well as anybody interested in this topic, to kind of come more fully into understanding the relationship here. So we've actually started a chapter of the Society of Catholic Scientists on campus. So you've got Dr. James Branish is our president, I'm the vice president, Dr. Chris Payne, and this is our secretary, Dr. Valerie Plaus, who's our speaker today. And we actually have a total of 10 different faculty, I think 9 or 10 different faculty here on campus that are currently members of the society. This is something that we take very seriously in what we do, and we want that to become more available to you, more approachable to you. And so how can you get involved? It turns out the society, both at the chapter level and at the national, international level, is not just for scientists, but there is ever-increasing interest in involving students. And so you can attend the rest of this seminar series. Again, welcome tonight, but please pay attention. We've got another seminar 2 weeks from now on the 2nd. And there's going to be an excellent speaker then by the name of Dr. Me. And this is going to be an ongoing thing. We actually have a handful of additional talks, and I'll show you that schedule in a little bit. But you can also attend national meetings as well. The national meeting is going to be open to students. You can actually even give a presentation if you're interested. And we've had now, let's see, I think this will be our 5th national meeting, well, really international meeting. And you can see some of the topics that we've talked about at this level. So who are we? What is the human mind? What does it mean to be human? Last year was a meeting about aliens.
Yep.
And
AI.
And artificial intelligence, and trying to understand how we can continue to understand our own role in the universe, given these additional understandings of the world around us. And actually this year at Mundelein Seminary, just north of Chicago, the topic is going to be Earth and Environmental Stewardship. And again, you're all invited. All you have to do is register to be a member of the society. It's about the cheapest society you could ever sign up for. I think student membership's like $20.
Yep.
And this is drivable distance. And I'm sure if you talk to the right people, you might be able to scrap along a little bit of money to get a van full of students out here this summer.
In terms of conferences that I have ever been to, this is pretty close to the bottom, because they find you cheap ways to do where to stay overnight and for the actual cost, and like food is relatively available. It's a really great event. And this time we'll be at a seminary, so that's cool.
Yeah, so please keep your eyes and ears open for those deadlines, and if you're interested in attending anything, feel free to reach out to any of the names you saw on the previous slide. Today's speaker, to me, Dr. Branish, any one of your faculty will be able to help guide you into trying to figure out how you can get more involved as a Catholic within this greater society. So again, our chapter right now, this semester, we're emphasizing the seminar series to kind of foster this culture, this appreciation for science and faith. A couple of weeks ago, Dr. Branish gave a talk on the origin of life, whether it was actually miraculous or not. Today we're going to learn about creation and cosmology, and you can see a couple of the upcoming talks later on. And again, boy, March 2nd is going to be a pretty good talk, I understand. So the schedule, we'll be posting flyers constantly, so keep your eyes out for updates, but I saw someone take a picture. This is kind of what's coming up.
Yeah, and just a quick note, Friday, it says Friday, February 11th. That's got to be the 18th, right? Yeah, okay. So this Friday at 3 p.m. in the Gentile Gallery is our invited speaker. So this is the School of Natural and Applied Sciences and our on-campus chapter, right? We both did it? Yeah, we both sponsored to bring this person in. So this will have a feel of, I guess, a history-like talk to sort of show how people in history have been both people of faith and people of science, and how that has worked to constructively build a society.
All within a Franciscan context.
Yes. So it's like all the things.
Yeah.
All the things. Those of you who've been in my class, that's what I say.
Anything else to introduce?
Nope.
Okay, so without further ado, yes.
One last thing before you leave. I have these surveys here. Can you please just pick one up and complete it before you leave? We need it for the...
It's really, really short. I mean, like 3 questions short. So if you can fill those out, that'll be great, because part of our series is paid for in part by the John Templeton Foundation. So this is part of our data collection for them. For those who just stepped in, there's also food.
Yeah, all right. So without further ado, Dr. Valerie Plaus will be talking about creation and cosmology.
All right. So,
This out.
oh yes, thank you. Sorry.
Stay away.
Please don't fall asleep, although there will be many pretty pictures. So the plan today, so I'm going to have to tell you what cosmology is, hopefully at some point. So what do science and the church both say about how the universe became what it is now, at this point in time? And we're going to have some fun defining time as we go forward in time. All right, so what does the Catholic Church say about creation of the universe? What is creation? Like when I talk about creation as a scientist, to what am I referring? And then what do we say about the evolution of the universe? There's a really cool person who I'm going to talk some about. He is both a priest and a scientist. He is also called the father of the Big Bang. We're going to talk about some different experimental ways that we have measured what's happening in the universe. So there's going to be some more fun pictures about that and some more physical principles. So what does the church teach? So if anyone's interested in these pictures and where I got them from, there's a slide at the end that gives you a list of all the images. So yes, copyright is important. All right, so creation in the church. First place to go, Catechism of the Catholic Church, paragraph 283. So what the Catechism says, and it's important here to look at the wording that they're using, the question about the origins of the world and of man. So the origin, what we're talking about there is, in philosophy terms, what is the cause of creation, right? Not necessarily what is the physical movement here, but what caused creation to be rather than to not be. Because that question is not defined by physics. Why there's a universe or not a universe, why the universe is what it is not a question that falls under physics. It's a question that falls under the philosophy of metaphysics, i.e. beyond physics, or around. What is meta technically? It's above, isn't it?
It's after.
It's after.
Beyond, yeah.
After, beyond. Okay, cool. So what I love about this statement here, these discoveries invite us to even greater admiration for the greatness of the Creator, prompting us to give him thanks for the understanding and wisdom he gives scholars and researchers. So our search for understanding of our physical universe is naturally ordered towards looking for a creator and looking for the why and inspiring wonder in our universe and the fact that we exist in it. So the Catholic Church focuses on the origin of creation, i.e. the philosophical cause of, which is God the Creator, rather than the natural laws that govern its beginning. So it's a different question to ask why the universe is versus how did the universe evolve? Or what is it doing now? Or what was it doing then? So those are different questions. And the fact that we're separating those two questions will show up in multiple things as we go forward. All right. Awesome. The type changed. All right. So what is the universe? There's more than what we just see, right? So there's the stuff we touch. There's the stuff we interact with day to day. There's the things that we can visually see that interact with photons, and so you shine a light on them and look, there they are. So the visible universe is only one part of what we live in and what we interact with. It's the part we see all the time. It's the part we're used to looking at. The stuff that we're used to looking at is roughly 4.6% of the universe. 4.6%. So our experience of the universe is based only on 4.6% of the information available and the content of the universe. It's also more than just the stuff. So this is the stuff. This is the content of the universe. So the content being physical and things that interact with physical things. So atoms are physical, dark matter being something you can't see, hence dark. That's literally all it means. We don't know what it is. Dark matter is some type of material that has mass, right? So like I have mass, tables have mass, the earth has mass. They are affected by gravity. But dark matter is not affected by anything else, just gravity. So it's really hard to measure because unless you can like point out where it is, how do I know what it is? So we just have some stuff that interacts under gravity. And this dark matter is still an ongoing question. We know a few things about what it's not. So it's not like, hey, there's lots of black holes that we just can't measure. It's not black holes. It's probably not neutrinos. Can't really tell you much more at the moment. And then we have this other stuff that's not tangible stuff. It's not gravitationally interacting. It's not strong force interacting. It's not electromagnetic. It's what we call dark energy. So imagine photons, but not light. And that's all we know. This is dark energy. We haven't found a way to measure it. All we know is that roughly 70-ish% of the content, in quotation, of the universe is this kind of energy that we have no way to measure. Okay. The other thing I want to talk about when I talk about creation and the universe is not just the stuff in the universe, it's the actual space-time of the universe. So things can't exist unless you have a space for them to exist in. So there has to be some type of what's called a manifold, some type of thing that stuff can exist in, right? Like there's no inside unless there's some type of building. So there's a tapestry that you can paint on, if you want to think of it that way. So you have the tapestry of the universe being space-time, and then you can put stuff on it or in it, and you can use that to rearrange things. So you've got this fabric, and that's literally what it's called. It's called the fabric of space-time, that we can change the shape of. We can change its curvature, which is what is described by Einstein. We'll talk about in a second. So you have this tapestry that you can put things on. And so that's what I mean when I talk about the universe. I don't just mean the stuff that you can pick up and put somewhere else, or even the intangible stuff that you can't really grab, or even the dark matter, which we don't understand what it is, right? All of this exists in space-time, and space-time is a tapestry that can be changed. The fact that it can be changed is new. So the fact that space-time is a thing that can change really started with Einstein. Here, dude, picture. Okay. This is actually Einstein posing for a picture with Monsignor Lemaitre. He has like 4 extra first names. So everybody's referred to by their last name in case you're curious and want to look them up. So Father Lemaitre was a mathematician, physicist, astronomer, and priest. He was not a priest of a particular order. He was akin to a diocesan priest, but he never had an assignment as a parish, like at a parish. So he was a priest. He had all the orders of being a priest, but his work was as a scientist. So he was a priest, right? He had the vocation, but a lot of what he did in terms of work was work within the church furthering science. So he was assigned, he did classes, he did research, all of those things. So he was a contemporary of Eddington. So Eddington was his PhD advisor, in case anyone cares. Einstein, right? So here in the picture, obviously contemporary of Friedman, Hubble, and De Sitter, whose names will show up in just a second. So Einstein proposed that not only does the universe consist of the stuff in the universe, but the universe consists of this space-time that can be affected by the stuff. So like when you paint a canvas, right, you saturate the canvas and the canvas itself becomes part of the painting. And so the paint and the canvas affect each other. The texture of the canvas can affect what you paint, and the paint itself can change the shape of the canvas. So this is the fun math. This is called Einstein's field equations. These are tensors. These are indices. All this means is that we live in space-time that has what we call 4 dimensions, right? The 3 that we're used to, right? Forward, backward, up, down, left, right. So those are 3 dimensions. You can move up, down, right? I'm not going to jump in place. Up, down, left, right, and forward, backward, which I can't do because there's a podium. But we also move in time. Now, we as the fun and interesting beings that we are only move forward in time. So that 4th dimension is a kind of rough one to talk about, but there are 4, right? And so these are matrices for those of you who are or have taken matrix theory. So these are just matrix equations that are solvable. And that is what Father Lemaitre did, or Monsignor Lemaitre did. So the formula here, this was Einstein's field equations of general relativity. That was 1916 that he published that. The first solution was by De Sitter. Now, De Sitter's solution of this equation is akin to what we call the trivial solution, which is like, if I don't put anything in, all of my equations work. So if there's no stuff in the universe, if the universe is empty, that was his solution. So De Sitter space is like the most straightforward solution of, I was going to say boring, straightforward solution of these stress energy tensors. Okay, so that's one solution. And that's why he was like, oh, cool, I can do that with math. Here we go, about a year later. The next ones were Friedman. So what Friedman proposed here in 1922 and 1924, so he had 2 separate publications, but did roughly the same thing and said, okay, if I put some amount of stuff in the universe, like a uniformly distributed amount of stuff, can I solve the equation? And so he proposed one, but one of the things that I thought was interesting in Friedman's equations is that the universe had to be expanding. If you put stuff in it, it had to be expanding. And then Lemaitre's, his solution was interesting. So De Sitter and Friedman were primarily theorists. They were mathematicians. They were like, cool math problem, can I solve it? Right? Not the same thing as what Lemaitre did. So Lemaitre was working with astronomy, right? He was a contemporary of Hubble as well. So this was at the same time that Hubble was working on things, which we'll talk about in a second. And so he was looking at the math and looking at the data and saying, can I come up with a math solution to these formulas that also makes sense with the data? And so his solution was data inspired. This was like a synergy of the math and the physics, which is the best place to be. Before I move on. So one of the things that I wanted to talk about Father Lemaitre, he did his primary education in Europe, and he had a professor, advisor person, whose name was, let me find it, Father Verreau. So this was in Brussels. Father Lemaitre is Belgian. So Father Lemaitre has this thing, and I get excited about this as well. If you look at the creation story, right? The 7 days. The first day, light and dark, right? So if you're looking at the evolution of the universe, the fact that light exists is one of the first things that happens. And so there's a lot of synergy between like the days of the creation story and different phases in the evolution of the universe, which we'll talk about in a second. And so he was getting all excited about this, and his advisor said, if there is a connection, it's a coincidence and of no importance. And if you should prove to me that it exists, I would consider it unfortunate. It will merely encourage more thoughtless people to imagine that the Bible teaches infallible science, whereas the most we can say is that occasionally one of the prophets made a correct scientific guess. And I love that statement. So this professor was also a priest. And what he's pointing out is that the truths that the Bible teaches us are different from, in terms of quality, or not quality, characteristics, right? So if we go back to the beginning, when we talk about what the church teaches about creation, it talks about the origin, like the prime mover stuff, is what is the cause of the universe. And what Father Verreau is saying is that if science does something, we need to make sure not to extrapolate too far into the theology. And we need to make sure that we don't extrapolate too far from the theology into the science, that we need to use the tools proper to each trade and look at the synergy and be awed by that, but not to suggest that one could take over the other's field. So I love that quote, and it sort of reminds you to be humble when you're studying something, to keep yourself in the right lane, to say. So what I love about Monsignor Lemaitre is that he's here and he's got one foot in each lane. He's a priest and he's a scientist mathematician. And there's a great story later on. I don't have the full text of it, so I didn't want to put it in here. But Pope Pius the 23rd? Let me find it. Hang on. 12th? Yes, I don't remember my numbers. Pope Pius the 12th. It's John the 23rd. Anyway, Pope Pius the 12th got really excited about these solutions to equations and was like, what they have to do with the universe. And he wanted to make a statement about it at a conference. And Lemaitre actually traveled to see the Pope and said, please don't do that with my work. Like, my work can't say theological things. Please don't do that. So it's nice to see that you've got feet in both lanes, but being aware of how the boundaries touch but don't overlap. So the solutions, back on track. The solutions to Einstein's equations here. We have a couple different solutions that could make sense. We have a universe that has a beginning and it expands, but it's kind of like when you throw a ball up in the air and eventually comes to rest and then comes back down. This is what they call the big crunch. So you have a bang in that the universe expands, but that there's too much attraction between all the stuff in the universe, and that space-time collapses again at the end. And so what you get is sort of like this periodic universe, which is like, I exist, and there are galaxies and stars and things, and then I fall back together, and then there's another crunch, and then I expand again. It's kind of like an oscillation, right? There's another kind of decelerating universe where you asymptotically come to rest, right? So this is assuming that the fact that you expand and everything is going in all directions, but that you're slowing down because gravity pulls things back together, and that the two of them are very well balanced. So that's one kind of decelerating universe. So asymptotically meaning eventually stops accelerating, stops expanding. I liked this one called the coasting universe, because this is just like everything's expanding at the same rate forever. Nothing else happens, just chilling, right? So the expansion rate is a constant. So these are all mathematical solutions. This one's the funkiest one, the accelerating universe, where not only is space-time expanding, but it's expanding and it gets faster. So in this first situation, right, gravity pulls everything back together and you come back into one point. In this situation, there's more repulsion. So pardon me as I go backward a couple slides. This picture, the dark energy, we get this percentage based on the acceleration rate of the universe. We can't measure the dark energy. All we do is like fit the acceleration and expansion of the universe and say, here's some stuff that's causing that. We're going to call it dark energy. That's all we know. So these are the different solutions that we have. And so what we do is we say, okay, these are all mathematically valid solutions. How do I figure out which one of these, and I'm kind of foreshadowing the whole time, which one of these universes we're in? Which one of these mathematical solutions correctly represents our universe? So, this was the thing. 1929, Hubble published his paper, and he said the universe is expanding. This was definitive data that showed that objects in space were moving away from each other. So I need to explain how he measured that, because it's not like he could say, where is that galaxy or that star, and be like, go out, walk over, measure it. Walk over, measure it 2 years later. Oh, it's farther away. That's not how this worked. So we need to talk about Doppler shift, or redshift, as it's referred to with light. This is the sticker that I really love. I want to get this bumper sticker, and I've wanted to for so long. If this sticker is blue, then you're driving too fast. Those of you who say this understand what this means. All right, so what this means is if you are approaching something and you're looking at it, light is reflecting off of stuff that you look at. You can't see things without reflecting light off of it. If this sticker is blue, that means that the two objects, right, your sticker and you, are approaching each other. And so as the light is reflected off, right, when I run into that light, I perceive that it's a different color when I'm traveling at it. So here's a fun picture. Right, here's our galaxy that's traveling away from us, and here's our telescope. So if this galaxy is moving away from us, each maximum of the wave, right, light is a wave, so each maximum is more spread out. And so as something is moving away from us, those wavelengths are more spread out. That's what we call redshift, simply meaning that the light looks redder. That's all it means. So if it's traveling towards us, it would be blue shifted. So if the universe was contracting or collapsing, you would see all the stuff around you blue shifted because it's all coming at you, right? Kind of like all of the material in class. It's all coming at you, not running away from you. So that's the two different descriptions here. So this is Doppler shift. Those of you who have never really, well, you can't say that. All of you who experienced this with sound, right? Whenever an ambulance drives by, right? It's higher frequency when it's coming at you, and then it passes you, and then it's a lower frequency. And when I've taught this subject before, I'll occasionally run around the classroom with this tone generator so that you can hear it. Our classrooms are too small to do that, which is sad. But the idea is the same. So you can do this and you can look at things and say, is it redder than I expect? Or is it bluer than I expect? And it's kind of hard to see here, but what we do is we say, okay, stars are made of hydrogen. And I can put hydrogen in a lab and I can see what colors it makes. And I know those frequencies. That's emission spectrum or absorption spectrum, right? You just diffract the light. Those of you who have taken this class, right? You know where the little lines are. The lines are at these angles. And then you look at space and you look at a specific galaxy and say, okay, did all the lines move redder or did they move bluer? And from that, right, the shift in the wavelength, how much extra wavelength there is, I can figure out this fun thing called the redshift. It's just a percentage. What fraction of the speed of light is something flying away from me? And so what you do is you just take a telescope and you go and you look at galaxies and you look at stars and say, what is the wavelength? This is his graph. Those of you who have been in my class, there's something wrong with the graph. Does anyone know what it is? It's okay, this is not actually class. The left-hand axis there says velocity in kilometers. It's actually kilometers per second. But think about this. This was really before computers. All of the graphs were hand-drawn. So you can't really fix it that easily. So later publications, he fixed the axes. So these are a bunch of stars that he measured. And he said, this is what their frequencies are. And he noticed the farther away they got, the faster they were going. So Hubble's law is that the speed of an object increases with its different distance. The speed of the object is proportional to how far away it is. And this is in parsecs. So this was 1929, right? 1929, before computers, all they had were some slits that they diffracted light through in telescopes. 2002, this is the new graph. The little red section down here, that's Hubble's original experiment, is this small region down here. So 80-ish years later, This is the data that exists now. And it's still on the same line. So Hubble's measurements were just looking at stars. It's still a Hubble diagram. Look, the units are better now. We're now in megaparsecs instead of just parsecs. And what we're doing, in order to see something so far away and have it be bright enough to measure, we have to look at supernovae, which are like explosions of stars. The only way we can get something bright enough to measure is to look at an exploding star. So it's the same graph. It still measures the Hubble constant. The proportionality still holds. Things are still moving away from us. All of the universe is moving away from us. So this proposes one of two things. One, the Earth is special, and we are at the origin of creation, and everything moves away from us. It's a viewpoint. The problem is, physics tells us nothing about making the Earth a special location in the universe. So the other possibility is that everything is flying away from everything else. If I did this experiment on a different planet, I would get the same answer. And that is what's consistent with the data. Not that the Earth is special, but that everything is flying away from everything else. And the only way that works is if, remember I talked about the tapestry that the paint's on? If you take the whole tapestry and stretch it, the whole picture gets bigger. It's like when you zoom in on something, right? Everything gets bigger in the same proportion. So that's why it's important to talk about space-time as being part of creation. It's not that the objects inside the space-time are stretching. It's not like I have a painting that's this big that's not attached to the canvas that I can zoom out. The painting is attached to the canvas itself stretches. So this is the cool thing. All right. The universe is expanding. If it's expanding forward in time, can I turn this logic around and extrapolate backwards? So if I'm expanding now forward in time, if I look backwards, do I contract? And the answer is pretty much. So there's an important thing to talk about here. So if you were just to say, okay, like we have this linear expansion in space, yay, there's a great fit for that. The problem is if you try and take that backwards in time, we run into some issues. And the first issue that's measurable is something called the cosmic microwave background. So the universe is expanding. The first indications that there was this special point in time was this map called WMAP. It's the Wilkinson anisotropy, Wilkinson isometric anisotropy probe, something like that. I don't know. All right. So the fact that there's this weird background to the universe that's not the dark energy, that's not the dark matter, that's not visible space, there's this other background, was first postulated by Alpha and Herman, and their publication didn't get a lot of noise. So it was just published in a journal, and no one paid attention to it until the 1960s. Which happens a lot in science when there's no internet, right? Like things get published in journals and never go anywhere. So if the universe is expanding and you turn around and you look at the universe contracting, at some point, if you remember thermodynamics, for those of you who've had it, if you compress stuff, it gets hotter. And so if you keep compressing stuff, at some point, atoms get so heated up that they become plasma. Right? So if I turn around and I start with the plasma and I look forward in time, and the universe is expanding, at some point the plasma turns to atoms. That's what we call the universe becoming transparent to photons. And at that point, the photons just expand and do whatever. This background, this microwave background, are those photons. They're photons from the early universe that we can measure. So this is the photon, proton, electron soup that was the universe. As it expands outward, the protons and electrons bind and become neutral hydrogen atoms, and the photons are left on their own to expand into the universe. Okay, so here's the weird part. This map, WMAP, first done in 1964, and then this previous slide, this previous slide was Planck's experiment. I think it was only 3 or 4 years ago. Show us that the universe expansion can't be constant. The temperature of these photons, the energy of these photons, tells us that the universe expanded faster than we thought it did at one point. Otherwise, they would be a different temperature than they are. So there's this weird part of time called inflation. So here's the universe. This is the space-time stretching. Here's our something happened Big Bang, right? There's an initial start. We can't really extrapolate backwards, but we have this point in time we can get back to called inflation. So here's the universe. That's the WMAP measurement map that I showed you. So like, okay, contract space, contract space, contract space, contract space. Cool. The dark ages, so named because photons couldn't propagate without interacting with stuff. This cosmic microwave background was roughly 400,000 years. That's not years ago. That must be after the initial. Okay, that's weird. Anyway, so you have this point in time where all of a sudden the photons decoupled, is the fancy word, from the rest of matter. So the energy and the matter became separate. And this point in time happened sooner ago than we expected. Right? Otherwise, if you were to draw this, right, it would go straight backward. Nope. So like pretend that these are straight lines and they would go backwards. Cool. But that's not what happened. We've got this weird spot here where everything expanded super, super, super fast. And we don't know why. Don't know. There are all kinds of models for inflation. That there's some reason why the universe expanded really fast at the beginning and then stopped expanding really fast. And like expanded at a relatively constant rate. And then for those of you in calculus, the curvature increases here. So now we're expanding faster again. Don't know why. Universe does stuff. We still don't have enough information to model and explain why the expansion rate of the universe varies with time. So the cool stuff, right? We talk about a Big Bang as like being an initial point, but what we're doing is we're taking in the normal universe and trying to extrapolate backwards through stuff we can't understand, right? Normal gravity, normal electromagnetism don't work past a certain point. This is what they call the quantum fluctuations. This is things get so hot that protons stop existing and they become quarks floating around in a soup. So you condense it even further, and everything breaks down and we have something called quantum gravity, which we haven't solved yet. So until we have a solution for quantum gravity, this whole section back here, we have no answers for. And so like a number of the people that I worked with in grad school are trying to model inflation and try and come up with a mathematical understanding of how that could possibly work. They're like, it's a phase transition. You're like, cool, of what? Mm. So like the idea that air has vapor in it, and if you cool down a surface, right, you get dew. That moment, that condensing, doing it in reverse, right? You heat it up and all of a sudden things vaporize. Can I explain to you why certain places I get dew droplets and certain places I don't? Nope. Why does space-time change its behavior all of a sudden? Mm-hmm. So this is our problem. We're stuck here in this space where we don't have an answer. Space, right? We're stuck here in the space. Yay! Okay, we got it. All right, so we're stuck in this universe that's made of space-time that we exist in, which makes it really hard to study because the stuff that we're studying is the stuff that we exist in. And not only that, but the rules that work out here don't work back here. So we have a universe. We understand that it's expanding. We understand that something interesting happened here and it expanded super fast. But we don't know why. And we don't know how. So where does this leave us? Still puzzled. So we're a little stuck right now, right? So we've got this space-time universe that we can tell you how it's behaving now. We can extrapolate backwards a certain amount to tell you how it behaved before, but that's really all we can do so far. We can go so far backwards in time and so far forwards in time to extrapolate things, but no further. And until we have a model that can predict more stuff, inflation is still a big question. We can't go further backwards in time than inflation in any reliable way. So the moments after what we call the Big Bang, we still don't know if there was something that was happening before that. Like, was there a space-time singularity that suddenly expanded? Was there something else that happened beforehand? It's like the inside of a black hole. We can't see it. We can't measure it. We don't know what's happening. So there's this event horizon in space-time that we can't pass, which is cool. So we've got this kind of way of like, it's masked the answer for us. And so until we improve our mathematics and we improve our observational abilities, this is where we're stuck at the moment. So this is cosmology, is the study of the history of the universe. And so where we are right now is a threshold a few milliseconds. No, I think it's 10 to the negative 12 seconds after the Big Bang. We understand up until that point. And then inflation happened, and now we're like, That's where we are. Questions and thoughts? I like this comic. So this is, anyway, sorry, yes. Dr. Kovac.
On the previous slide we had of the,
Yep.
I'm not understanding how like the first star appeared 400 million years ago. I mean, I thought the first stars were several billion years.
Yeah, it's working forwards. It's measuring forwards
So
from when we think the Big Bang was. Yeah, it's measured forwards in time, not backwards. Yeah. So this roughly 400 million years after the quark gluon soup. Yeah. So the part that's kind of hard to visualize here is that you've got this like really hot, weird plasma that expands and then forms protons and then expands and then forms neutral atoms and then expands. And then I have enough space for electromagnetism to be like, okay, I can chill. And then gravity takes over and things start to clump. And that's where the stars form, is when we get the clumps big enough to undergo fusion. Yeah.
So in the Dark Ages,
Yep.
is it entirely dark energy or question mark?
Okay. So the Dark Ages referring to here is, so you go from like neutral atoms, right? And those neutral atoms are spread out through space, and there's still photons. So there's still light, but the light's not really doing much, right? It occasionally hits an electron and excites an atom and then goes back down. But the photons are there. They're like a bath throughout the universe, occasionally interacting with hydrogen and then chilling. Literally, that's what's happening, is that the universe is expanding and cooling down. Yeah. So the Dark Ages here are the time after I had photons interacting with ions, but before gravity had clumped enough matter to create stars. So it's called dark because light wasn't being created. Does that make more sense?
Yeah, but that's energy. Where's dark energy?
That's the issue, right? Why does the universe expand faster here? Because that would imply that there's more dark energy now than there was here. Yeah. Why? Yep. So the cool thing that's happening is there is a recent article published that said that the universe is expanding 5 to 7% faster than we originally thought it was. And I'm wondering if every few years we're going to see like, oh, it's a little bit faster. Oh, it's a little bit faster. It'd be cool. Yeah.
Well, changing the rate of expansion there.
Yeah.
You can also bring some cyclicality in the rate of expansion. You can have some oscillatory.
Yes, exactly.
In the map of the different alternatives that you had before.
Yep.
This is not there, and maybe the oscillatory
There we go.
alternatives are not there either.
Yep. So that's this one here.
Well, this is like one only cycle, but if you have this change there in the rate,
yeah,
you may have something that goes up and down,
yeah.
the rate of expansion.
So something like this one, except that instead of having a nice smooth curve here, it's like expand and then slow down and then expand and then slow down and then expand and then slow down. Yep. So the contracting one is relatively well disproven at this moment.
No, but
yep.
I don't mean contracting to
a point.
Completely, but maybe having a rate of expansion, then a rate of contraction, then an expansion.
Right. So it is not disproven that the rate of expansion can oscillate, but it is relatively well disproven that it can't contract in any amount. right? So the acceleration is winning no matter what. The rate of acceleration can change, so it can accelerate outward faster or less.
Yeah, but you can never really tell that until you understand inflation.
Mhm.
Because if the things that created that inflation at some point,
Yep.
anyway, once you have a phase in the future that has something like that in a different direction.
Yeah, so if we could figure out what that was and have that, for lack of a better word, phase transition be in the opposite direction, then yes, you could do that. Since we don't know what that is, I can't tell you if that's possible or not. Yeah, Dr. Kovac.
Yeah, what's the best speculation of, assuming that one of us, for instance, for you, lives forever,
Yep.
and you don't have a theological number to do something, what would be there?
Right would be there.
Would be an increasingly empty
Yep.
space with increasingly less energy and
Mhm.
nothing left.
So the current thing is that if you extrapolate this picture forward in time, that there would not be a third generation of stars. So you've got this first generation of stars, and then we're in the second generation of stars. But the universe is expanding fast enough that there won't be enough gravity to clump the explosions of this second order supernovae back into another set of stars. So the heat death of the universe is what we expect. I can't remember the timeline for that though. So the expectation is, yes, space-time will continue to stretch until there's enough distance between objects that nothing interacts anymore. And you have cold, dark matter and photons.
Would time still exist?
Yes, as long as space-time exists, time would still exist. Under one of the definitions of entropy increasing being the definition of time going forward, I think that still works because you can still scramble the distribution of matter into a most probable cause, but it will like asymptotically increase. So time might slow, but I don't think it would stop.
It's one of the questions, what is time?
Yeah, all right. I was wondering that we get here. All right, so space. What is time? All right. So there's I'm gonna steal that question. I'm gonna run with it in a different direction. One of the common questions or common popular disproofs for God that Hawking put forward is that things can't exist. Like the universe, nothing existed before time because time is defined by space-time. So time is a part of the universe. So you've got like the physical space that we exist in, and then you've got the time that describes how it evolves. And so before the universe existed, you can't have time. So time I would describe as part of this tapestry in which things exist that describes how they interact. So time is not an eternal thing. So there's no before the Big Bang because there's no time, in quotations, before the Big Bang. So time is a part of the universe, just like space is a part of the universe. It is part of the tapestry. It's part of that existence. That's a kind of, I can't really describe what space is. It's a thing through which I move, and I would describe time in the same way. It's a thing through which I move. Time I move one directionally, space I can move into. Yeah.
So you had that picture from background microwave radiation.
Yep.
How did they get that? Like,
I love this
and
picture.
also, like, what exactly is it?
Yeah. So this is, if you point a telescope at any direction in space, you get light. This is originally what they thought of as noise when they pointed their telescope at stars, and they got like, here's the spectrum of the star. If they pointed their telescope just slightly off to the side, they got this noise. So this is space itself having photons in it. So you point the telescope anywhere, you get this microwave, literally like microwave frequency of photons that enter your telescope, no matter where you point it. So cool things about this bath of microwave photons that come from everywhere at us, which are just existing in space going in all directions, this background is relatively uniform. Right? There's hot and dark spots, but it's relatively uniform, which basically tells us that the universe is isotropic. It's the same in all directions. There's some places that are brighter than others, but it's not like there's nothing in one spot and everything in another. So if you look at how people tend to sit in a room, right, they tend to spread themselves out so that they have space. Right? You look at people, maybe on a bus. Imagine people sitting on a bus. They tend to like sit separately. This is what the universe has done, is it's relatively spread itself out. And the fact that it is so uniform, so isotropic, is our indication that inflation happened. So inflation happened. These photons exist in the universe, traveling in all directions, and they no longer interact with stuff. And so you point a telescope at them, and they're like, hey, doesn't matter where you point the telescope, there will be photons flying in all directions. Yeah?
Is there an approximate size or shape of the universe?
Okay, so one of those, okay, size. We don't know, because we can only see so far backwards in time with telescopes. So let me back up to this graph, right? This is how far we can see at the moment. Past this range, this might be a little bit further, but past that range, we can't see. So if I was to look at things that are really distant, first of all, they have to be super bright for me to see them. But also the further I look outwards, right, because it takes time for that light to get to me, I'm also looking backwards in time. So the issue that I have is that when I'm looking at size, I'm limited by time. And so I can only look so far backward in time, and so I don't know how big the universe is because I can only look so far in time to get that space because they're connected. The shape. So we live in 3D space. The 3D space that we live in is usually described as flat, in that there is no curvature to it. So like if you look at a piece of paper, I don't have one. If you look at a piece of paper, right, paper would be flat in that I can't curve it back on itself. So if you like take a piece of paper and fold it over so you now have a cylinder, that would be one direction of curvature. But you would see the paper, if you were standing on the paper, as flat. Like you could walk in two directions. As far as we can tell, the three-dimensional space that we live in is flat. So that you can walk in one direction. And it doesn't wrap back on itself. So as far as we know, it is flat in 3D. And that's actually related to the measurement for pi. So if you measure pi for a circle, if a circle is painted on a curved surface, then the angle and the radius and the circumference are related differently. So if you do this in spherical coordinates, remember how the azimuthal part, that radius is a different shape depending on your angle? So you get a different ratio for pi than if it's on a flat circle, if it's on a flat surface. So that measurement gives us a good, reliable understanding that the universe is flat. Yeah?
How is counterintuitive that the universe will be expanding and isotropic?
Yep. That's our assumption at the moment, and that is well substantiated by this map. That it's isotropic, relatively uniform, but also expanding. So this expansion will stretch, but it won't clump.
But the nature of something expanding is direction.
So, yeah, no, I'm not laughing at the question, but this is a fundamental issue for humans because we don't see ourselves as stretching. Like when we grow into empty space. The universe is not growing into empty space. The stars are not expanding into space that already exists somewhere else. Space-time itself stretches. There is no outside for us to expand into. So when we say that it's expanding, I mean that space-time is stretching and the distance between objects is changing, but not that I'm expanding into something else, right? It's not like an overflow room at church. You're not overflowing into something else. The church itself grows and stretches, and so the pews become further apart. Yeah.
Yeah, but you measure distance between objects.
Yep.
If the universe is expanding, so the distance for any object that you want to choose to the object that is farther the weight
Yes?
cannot be the same. It is expanding.
Correct. The
So
distances
if
are
that-
changing.
If that fact
Uh-huh.
would bring something different than something is isotropic.
So
For example, the number,
Yep.
the level of noise
Yep.
closer to the frontier has to be different from the noise in the center.
Nope. So if we're looking at this map, right? If the amount of noise was different in the center than the outside, what you're saying is that the outside is expanding faster than the inside. But the problem is that space doesn't have an outside and an inside for that to make sense. It's not like a pie where the outside cooks faster. There is no outside and inside.
But you draw it, you yourself, when
Uh-huh.
you go to your picture of,
Yep.
of the expansion in the face here,
Yep.
there you draw a center and a perimeter.
Yes.
Right?
Because we are limited to our understanding of space-time. We're trying to draw something in 3 dimensions that we experience in 3 dimensions that we can't draw a 4th dimension to see it expand into. So it's a limit of our understanding being 4-dimensional beings in space-time.
And what's the meaning of the distance in those charts in which you have distance
Mm-hmm.
and what was it, the color?
This one?
Here, yes.
Yep.
So what's the meaning of distance?
Just distance from us. So we're using us as the origin of the system and measuring away from us. But I could do the same experiment on any other planet.
Have we?
Have we? Not yet. I know. Mars is not significantly different enough to be able to generate a different plot. Because if I'm measuring out to megaparsecs here, I would have to put another sensor megaparsecs away, which would take, I think, several millennia to get it there. And then it would take several millennia to get the data back. So the problem with this boundary, this Hubble diagram, is that I can't talk about expansion outside of what I can see. And it takes so long to get information to that point and then back from that point that there's a limit to what I can know. And that's called the Hubble radius. Is how much of the visible universe I can see. Yeah. Yeah.
So why do we extrapolate this out?
Because we would like to see if it could work. Yeah, so why? Why do I expand this to the inner universe? So what I can see of the universe tells me that my space and someone else's space are relatively similar. So if I was to do this experiment somewhere else, I should get the same answer. So if I do that, then I would expect to see my own graph like this in a different place. So this is the definition of a manifold, where I take one location where physics applies, and I assume that a neighboring location, which appears similar and works similarly, also has a space where physics applies. And I just take small steps sideways and assume that if it works here, and here's a place that I can observe where it works, this is called like a linear extrapolation, right? You move a little bit over and it should still work. And you move a little bit over and it should still work. So we're extrapolating this to the entire universe because we believe that no one place is drastically different than any other place. So because we're scientists, I must accept the possibility that outside of my visible universe, outside of the Hubble radius, there is a place where the physics could be entirely different. And I don't know. And then all the rules fall down. But as a Catholic, I believe that our God, who is the Logos, makes sense. And if he wants me to understand the universe in which he's placed me, that I am going to trust in the rules that I can discover, and that I will learn from them and be able to extrapolate truths about the universe from what I can see right now. Yeah.
So does it require an actual changing of physics or just a changing of the observable phenomenon?
Ah. Because the observable phenomena is based on physics, I think the answer is yes to both of those. If it can't be either or because the observable phenomena are based on the physics. Yeah, Peter.
So on this diagram,
Yeah.
As the distance from us or from anywhere,
Mhm.
speed.
Yep.
everything from any observer,
Mhm.
things are limited by the speed of light.
Yep.
If we expand this, if we assume that this keeps going on
Yeah.
forever,
Mhm.
when we get to the velocity of the speed of light,
Yeah,
does that
over here.
limit the distance that the universe can keep?
Correct.
Okay.
Yeah, so there would be a limit. There's a limit to how fast things can go, and therefore there's a limit to the physical size that I can extrapolate here. But this is all the data we have so far, and as you can tell, hang on, I can do this. 1/10,000th of the speed of light at the moment. So we're not even in special relativity world.
It's been a long time.
It's been a long time. Dismals. Other thoughts and questions? We're over the technical hour in case people need to run. Yeah.
So again, based on this graph,
Yeah.
just a kind of thought question here. So the supernovae, they're farthest apart.
Mhm.
The light that's reaching us now is billions of years old.
Correct.
Right.
Yep.
So doesn't that argue that things were expanding faster earlier in the universe?
That's what we would think, right?
Because things that are far away are moving quicker, and things that are closer are moving apart.
You could also turn the thought process around. We could be moving away from them. And so sooner in time is expanding faster than earlier in time. Because we're expanding away from the thing that we're looking at. So it's not that the thing in past time is moving away from us faster. If you assume that this is your origin, being earlier in time, then us being later in time are the ones moving away faster. That one makes more sense to me because I usually think forward in time rather than backward in time. Yeah.
Why don't we formally wrap
Yeah.
things up and thank Dr. Plaus again, and if you have any questions, you can go up and ask her afterwards.
And I have lots of books if you want more details on something.
So let's all say thanks again.
Always able to
Thanks for
comment.
coming, everybody. March 2nd, next talk. It's going to be really good.
All right, how do I stop recording?